So we'll continue with the part 2 of the phi layer. We were on this slide last time and we will redo that one. So there are 3 terms here: element, baud and bits. You need to understand the difference between the 3. So this bit consists of 2 elements, a long pulse and a short pulse. That is one bit. If you want to send a 1, you send a long pulse followed by a short pulse. Okay? If you want to send a 0, the coding will tell you what is the code for 0. It could be that it is a short pulse, 2 short pulses maybe. So the coding will tell you what a 0 looks like, what a 1 looks like. 0 and 1 do not have to be just 5 volt and 0 volt. So these are elements. And this is a bit. And here the coding is very simple. It says that you could have minus 5 volt or plus 5 volt. So, and in some cases the coding says that it is not the level, it's the transition which makes 0 or 1. So if we transition from low to high, that is a 1. If we transition from high to low, that is a 0. Actually, sorry, this is shown slightly wrong. If we transition, so this is the bit, this is a bit. In this bit duration, there is a transition, that is a 1. If there is no transition, so this actually does not really show a 0. If it was continuing here, then there is no transition during that bit time. That would be a 0. Alright, transition is a 1, no transition is 0. And there are many different kinds of coding, and there is advantage and disadvantage of each kind of coding. Okay, and we will learn some of them. But anyway, so the idea is, in each of these cases, there is a smallest element that can be, so in this case, for example, the smallest element can be equal to 1 bit time, right? And that is called a baud, right? In this case, there are 2 elements. One is big, one is small. The smallest one is the one that tells you how much is the baud rate, because the smallest element determines the quality of electronics that you need to use that coding, right? If it is very small, nanosecond, then you need much better electronics than if it is millisecond. So the baud rate determines the quality of the electronics, and the bit rate is what you are interested in, right? The electronics doesn't really know the bits, but what they know is, and so how many bits are coming out is what you are interested, as a user you are interested in, but the electronics quality and price depends upon the baud rate. And some combination of elements actually is called a symbol. So I didn't want to use the word symbol here, but we could, for the time being, we would call this one thing as a symbol, because generally when we go into the later part of coding, you will notice that we don't send a bit actually, we send multiple bits at a time, a bunch of bits at a time, and that is what we generally call a symbol. So we'll come to that in a minute. So we'll reserve the definition of symbol. And so we'll have element, baud, and bits, right? Okay. Now, if we just keep sine waves so I just showed you some square waves, but let's forget that for a minute and just think about sine waves. If you have a sine wave, then you can modulate it in different ways. So for example, if the amplitude is small, that is a 0. If it is large, it is a 1. 1 is 0. Okay? So that would be called amplitude modulation. When you want to send a 0, you just send a small pulse, small waves. When you want to send a 1, you send big, high waves. Or you could change the frequency. So when you want to send a 0, you have a low frequency. When you want to send a 1, it is a high frequency. That is frequency modulation. Or you could change the phase. When you want to send a 0, the phase is 0. When you want to send a 1, the phase is 180 degrees as shown here. Yeah. Last one?
Yeah.
Yeah, okay. So basically you have to determine what is the phase of this pulse, of this wave. If phase is 0 as shown here, then it is a 0 bit. If the phase is 180, then it is a 1. You see, this is a phase. At the beginning of the bit, we generally indicate the waves will go up, right? But it is going down. So phase is 180. Yeah.
Do you know which is the fastest of these to do to modulate between the 0 and the 1?
Which one of the amplitude, frequency, and phase? All right. So the question is, which one is the best? Amplitude, frequency, and phase. I would simply say which one is the easiest right now, because best would come out later, right? So the easiest thing is amplitude, right? If I say loudly, then you can easily calculate, you can see that the amplitude is high, right? And if I say slowly, then it's a 0. And so that's the easiest thing to figure out. Amplitude can be easily figured out. And then frequency is kind of difficult. If I say in a very tiny sound voice, then it is a 1 and a 0. So in general, for example, female voice is much higher frequency. And so that is difficult. We can still, human beings can figure out in female and male voice. But at the electronics level, it kind of, becomes more difficult. And the phase is even more difficult. Okay? And now the question is, which one is best? Basically, I haven't defined the best yet, so I'm not going to say, but basically it is very easy to interfere with the amplitude modulation. Alright? Frequency modulation, it is very difficult to interfere with, because if you introduce exactly the same frequency, then it is different, but if you introduce any other frequency, I can easily filter it out with a frequency filter. Right? So you will not affect my zeros and ones. So frequency, you can see right there that the frequency modulation is better. The more difficult things are generally better, right? So what it is the life started with amplitude modulation. We call it keying here. In a minute I will explain why keying and what is the difference between keying and modulation. So life started with amplitude, and then people felt, no, we can also do with frequency. It is better in some sense, but more difficult. And then they said, why can't we do with phase as well? Right? Now, why we call it keying as opposed to modulation? Modulation is generally for the analog, continuous variation. So suppose you want to send a sound like we used to do before, telephone. We used to modulate the sound on an electronic sine wave and send it through a wire. That would be modulation. But now we don't send the sound that way. Now what we do is we take your sound and make it zeros and ones. So we make 8 bits out of each level. And then we send zeros and ones. So we call it keying. Keying is basically 0 and 1, binary. Okay? So when I say ASK, it is binary. When I say amplitude shift modulation or something, then that would be continuous wave that can be put on a sine wave. Is that clear? That it doesn't have to be 0 or 1. The amplitude could change continuously. Yeah.
Is the difference there in how it's interpreted or the signal itself?
So the signal itself is in the case of modulation is continuous signal, and so input signal is continuous. The transmitted signal is continuous in all cases anyway, but the input signal has a continuous amplitude, and then it is modulated on some kind of transmitted signal, and then when it is received, we get back the original signal. Right, so that is modulation part, right? In the keying part, you send zeros and ones, and you get all this thing which is actually continuous, if you want to call it continuous, and then you get back the zeros and ones. Okay? Any question about this? All right. So now we can continue this. And so people felt that instead of zeros and ones, why don't we do differential, where you don't worry about the original signal, you just worry about the previous symbol. So this is a 0, and since there is a phase shift, this is a 1, and then there is a phase shift, and therefore this is a 1. Then there is no phase shift, and therefore this is a 0. So in this case, basically you don't have to worry about what the originally where the phase was, but basically the previous bit, if there is a phase shift in this bit, it's a 1, and if there is no change in the phase shift, then it is a 0. Yeah, question?
So could there be a problem if like one of those phases is lost and everything going?
No, actually you can't lose a phase. Basically what it is in this case, the clear advantage of differential is you can put a positive wire on the negative side and negative wire on the positive polarity, it's independent. Because you really are not looking for plus or minus, you are looking for a change. Okay, yeah, go ahead.
So all the time the first bit should be known at the receiver, yes?
Okay, so the question is, for all these cases, the first bit should be clearly known whether it is 0 or 1, because you could know. So in the differential case, actually, you probably don't need that. Because when there is a change, now this is a 1. Whatever the previous one was, of course, it was something different, right? So you know this one. But in other cases, in the previous cases, that was not differential, then there is a problem of synchronization that you really need to know where the bits start. For example, if you start the bit right in the middle here, there will be a problem, right? So so you want to synchronize the bits correctly, and then polarity is also important, because if you are thinking about positive and negative. And so what we do is in the beginning we do synchronize. So whenever you set up a connection, there is a synchronization pattern sent, and if you receive that pattern, then you know, okay, we are right on time now. We are receiving the bits correctly. Now we can do the communication. So that part we are missing right now, but basically let's assume that somehow we know where the bits begin, and we look for the transition at that point. Otherwise, if you look at the wrong point, you will get only a zeros. Right? I mean, there won't be any transition. So you have to be exactly aligned, and then also in some cases you need to know the correct phase and correct thing, and this and all that is done in the beginning. So now this is a differential. Now this is the name, and the name is important. Differential BPSK, binary phase shift key. Okay, so binary means 0 and 1 only. And phase shift means we are only going to find out between 0 and 1 by phase shift, right? And differential means only from the last bit, as opposed to from the absolute position, right? And you don't have to have binary, you could have quadrature. So what you could do is you could take 2 bits at a time, and 1 would be 45 degrees, 1 0 would be 135 degrees, 0 0 would be 225 degrees, and 0 1 could be 315 degrees. And so whenever you see this shift, in this case it is 45 degrees, in this case it is 135 degrees, in this case it is 225 degrees, and so on and so forth, you know what bits are coming. So now you can get 2 bits in the same time. So this will be twice as fast compared to BPSK. QPSK will be twice as many bits per second. The only complication here is, here we only need to know whether the phase is 0 or minus 180. Here we need to know whether the phase is 45, 135, 235. So you have to be able to distinguish between the phases much more carefully. Yeah.
So the error performance for the QPSK is worse than differential previous.
This will have very little error. This will have more errors. That's a good point. And one way to represent this, we won't be plotting waves anymore. We will be representing them on a chart like this, where 0 has a phase of 0 and 1 has a phase of 180 degrees. And in QPSK, 0, 1, 1, 1, 1, 0 and 0, 0 are shown right here. and you could put this 0, 0 wherever you want to, and then you tell the receiver that this is my coding, and they will get the same coding, but they have to distinguish between the 4 angles. Yeah.
Why would the QPSK does not have any zero representation when I say
0 here? Yeah, right. See, because basically you need 4 combinations. Now you could make 4 combinations here, like, you could do 2 here, 0, 180, 0, 90, 180, and 270. Right? And now, I think that should be equally good, but I really don't know. I mean, like this, in this example, it is not the case. Right? And most of the examples that we'll see, if you have 4 phases, they will distribute it like this. And maybe, there's some reason which I don't know at this point. Okay? But right now, when I say BPSK, you know that this is basically that, 0 and 180. They could have shown 45 and, 225 or something. And that would be equally valid, yeah.
May I tell the reason that why they're choosing this way? They choose in a way that the neighbors have only difference in 1 bit. So if the error happens, it's more probable that 111 be detected as 10 or 01. So we will have error only in 1 bit. So because of that, the code words that are different in 2 bits, they will put them in as far as possible. So if they, it will be less probable that they will get detected instead of each other. So the error will be decreased.
Okay. So let me say, I think you answered a different question, but that's an important consideration. So C asked the question, but why it is at 45 degrees and not at 0 degrees? And you answered another question, and that question is that these numbers are not arbitrarily put here. 0, 0 to 0, 1, there is only 1 bit change. 1, 0, 0, 1 to 1, 1, there is only 1 bit change. And 1, 1 to 1, 0, there is 1 bit change, 1 bit change. Because it is quite possible that you might mistake this phase for one of these two. In either case, there is only 1 bit error. Right? That's the question you answered, right? Yeah, so that basically means that you cannot put 0, 0 here and 1, 1 there. That would be wrong, because then you will get 2 bit errors, for a little mistake. But that question of 45 versus 0 degrees still remains. All right. Now, why stop at 4? Okay, so this is called quadrature amplitude modulation, QAM.
same as QPSK?
Eh?
Same as QPSK?
Yeah, same as QPSK, QAM. Quadrature amplitude and phase modulation. Now I will tell you why amplitude is coming in. But right now, in this case, there is no amplitude. All those 4 points have the same amplitude. What is the amplitude? Amplitude is the distance from the origin. So this point has an amplitude of that one. This point has the same amplitude. This point has the same amplitude. This point has the same amplitude. So all 4 points are different phases only. Right? But there are 4 points, so we call it 4 QAM. But you don't need to have 4. You could have 16. How 16? Because now we have 4 here inside and then we have these outside. So we measure what is the amplitude and what is the phase, and we then get 4 bits at the same time. Okay? With this we get only 1 bit at a time, in this we get 2 bits at a time, in this we get 4 bits at a time. Alright? But we have to be able to distinguish between a small amplitude and a big amplitude and a small phase and a different phase. 4 different phases. Actually, probably more than 4, because there is this angle, there is this angle, and there is this angle. 3 angles right there. So there are 12 angles. Okay? So now you see how we combine the amplitude and phase, and we put a dot there which says now this means 1, 1, 1, 1. Okay? 4 bit per each point. And so this is what is called a symbol. So here in 4 QAM you have 2 bits per symbol. There are 4 symbols. Here we have 16 QAM, we have 4 bits per symbol. And how many symbols are there? 16 symbols. Right? Now can you think of anything higher than that? Where will you go after 16?
64.
64. You can have 64 QAM, and then 64 times 4 is 256 QAM, and then 1024 QAM, and that's where the world is going. Previously, we could not do all these high-level QAMs because we didn't have that precise electronics. Even 4 QAM would require big vacuum tubes this large, and you need 10 vacuum tubes. Now with light, tiny transistors, we can do 1024 QAM and higher up, 2056 and whatnot. Okay, so we can send lots of bits per symbol. Okay, and when you send lots of bits per symbol, of course your error rate goes up, but if you have a good electronics, it will keep it controlled. Alright, so channel capacity, how many bits can you send? So, Nyquist theorem says that if your bandwidth is B, your data rate has to be less than or equal to 2B. What it says is that if your bit rate would be twice the baud rate. So here is the coding: 0, 1, 0, 1, 0, 1, 1 bit per baud, right? So the baud rate, now let's see. No, actually that's why I drew this. Hold on. This is 1 bit. This red thing is 1 bit. So the bit rate is twice the baud rate, or half the baud rate, whatever. So the thing is, here, this is 1 baud, this is another baud, 2 bauds that make a bit in this coding. And this is another bit, and so on and so forth. But you could do, instead of by level, you could do 4 levels. So this could be 0, 0, 0, 1, 1, 1, 1, 0, and basically what you would do is you would put the numbers so that there is only 1 bit changes at a time, just like we did in that phase diagram. You wouldn't just put 0, 0 here and then 1, 1 there, because it is quite possible for us to mistake that from that for that one in the levels, right? In this case, we are just talking amplitude. So you could do 2 bits at a time, and then you will have 4 levels, 1, 2, 3, 4 levels, and so on and so forth. In this case, you would be able to send, now, okay, here's the thing, I'm sorry, I'm a little bit confusing you, but basically, so there are 2 bits here, 2 bits here, 2 bits here, 2 bits here, right? And then 2 bits, 2 bits, 2 bits, 2 bits, and so every pulse is a 2 bit, right? And this is a baud. Baud is, let's say every pulse is 1 second, so then it is 1 baud per second, but there are 2 bits per second. So the bit rate is twice the baud rate, right? But what is a cycle? Now you notice that if you were to send this signal, the wire that you're going to send it through, it doesn't see any bits and bauds. What it sees is cycles, and here is a cycle. It starts from here 0, goes there, goes 0. Then it starts from there and goes there, right? So it's like a sine wave or something, right? And that cycle is how much? Is basically, if everything is 1 second, then the cycle is 1, 2, 3, 4, 5, 6, 7, 8. 1 cycle per 8 seconds. We have 2 bits per second, but 1 cycle of it. So basically, your capacity is 4 times the bandwidth. Now, so the bandwidth is 1/8 of a cycle per second, right? And 4 times that would be 1 half of a bits per second. 2 bits per second. Capacity is 4 times. So the cycle is 1, 2, 3, 4, 5, 6, 7, 8. 8 second. Cycle is 8 second long. 8 second long. But the bits are half second long. So we are sending 2 bits per second, but we are sending only, okay, there is a slight problem here. And the problem is that this is not the right cycle. So wire will not see this. What wire will see is the worst case cycle. So this frame is very good, but in the worst case, you could be sending things much faster, which is that you could be sending this, let's say, whatever this is 0, 0, followed by whatever this is, let's say 0, 1 or something like that, whatever, right? And then 0, 1, 0, 1. So your cycle should be much smaller. Okay? So think about that cycle. And that cycle will not be 8 seconds. That cycle would be just 4 seconds. 2 seconds low, 2 seconds high, 2 seconds low, 2 seconds high, 2 seconds low, 2 seconds high, right? Sorry, 1 second low, 1 second low, 1 second high, so it will be 2 seconds per cycle. So it is half cycle per second and 2 bits per second. That is 4 times. So the bit rate is 4 times the cycle rate. Alright? Cycle rate is called hertz. Okay? So you have half cycle per second is half hertz, and you are getting 2 bits per second. Right? So whenever somebody presents your coding, you have to take the worst case cycling in that one, and worst case in that one, how fast the things will change, and that is what is called bandwidth. Now here is the thing: lot of time computer scientists misuse the word bandwidth to mean the bit rate. But bandwidth is actually more coming from the analog days, and that is actually the cycle rate, the hertz rate, hertz. So the bandwidth is hertz. Okay? So you measure, and the wire really cares for the hertz. So what happens if you take a wire, its capacity is limited by how many cycles can go through it. Okay? So that's why we have this Cat 4, Cat 5, Cat 6, Cat 7, Cat 8, Cat is category, Ethernet cables. The higher the category, they have a higher cycle that can go through, higher number of megahertz that can go through it. Okay? So the wires are measured by the hertz. The electronics which is at the source and destination is measured by baud. And what you are interested in is measured by bits. And there are 3 people involved here. The sender, the user, the sending electronics and receiving electronics. So the electronics, the wire, and the user. Electronics is limited by what? Again, we just said, Somebody listen. What electronics is limited by baud. And the wire is limited by hertz. And the user is interested in bits. And there is no relationship in the sense that, can you have 2 bits per hertz? Answer is yes. We just saw an example here, 4 bits per hertz. Right? Can you have half bits per hertz? Yes. There are coding which give you only half bits per hertz. Okay? Because in those cases, you really want no errors whatsoever, so you are very careful. Okay? You get half bits per hertz means you send 2 cycles per bit. Okay? And similarly for the bauds. And so the bauds and bits. Now bauds and cycles may have some relationship because you cannot have, so let's say I think you can have 2 bauds per cycle. But you cannot have, maybe you could have 2 cycles per baud. Yeah, you could have that too. So basically, so one is not more than the other. Basically, it depends on the designer to put the relationship together. So when you design these codings, you have to decide how much electronics you want to put on the electronics, what kind of wire you want to use, and what you get out of it. Clear? So anyway, Nyquist theorem says that you cannot get more than 2 times the bandwidth if you use bilevel coding. If you use M-level coding, you cannot get any more than 2 times the Hertz rate times log 2M. Log of M base 2.
What is M?
Eh?
M?
M is the number of levels. Okay. Now I just gave you an example of 4 level, but you could have higher levels. In this 4 level, the main confusing thing is that this looks like a cycle. I should probably try another diagram with the worst case cycle for this coding. Okay, and that diagram would be where you are just jumping between high and the low. And so the cycle would be much smaller. Yeah.
What determines a channel in that case?
Channel. What is a channel? So basically, I mean, like generally we use channel for the whole thing, send all the way from sending electronics to the wire to the receiving electronics. The whole thing is called a channel, right?
Can you have multiple channels?
Yeah, so you could do multiple channels. I mean, you could have 3 wires.
Oh, but it's
4
one
wires.
channel per wire?
No, you could have 1 channel per 2 wires. See, the thing is, this is another domain, okay? So the question is, generally, you will have, depending upon the way you design it, you could have 2 wires and 1 channel. Because you will have positive and negative. So to determine that, you will need 2 wires, right? And then, for example, Ethernet wire has Ethernet cable has 8 wires in it. Right? 4 channels. Okay? Ethernet cable has 4 channels, and they are all in parallel. All right. So now we go to another theorem, Shannon's theorem. And Shannon says that depending upon how much noise you have, you cannot talk too much. So right now we are, I can give a very fast lecture and you will understand. But if it was, let's say, a fair with a lot of people, talking to each other and going around, then I couldn't talk very fast. Because if I talk too fast, you won't understand anything, right? So the bits that can be sent also depend upon the noise. And his formula is that if you take signal S and the noise N, measure them, and then take the ratio at 1, take log base 2, and multiply by the bandwidth, that is the maximum data rate you can get, maximum bit rate you can get. So here's an example. Let's say phone wire. Now the phone wire that we use for phones, that is really a poor wire. It was designed in very old days, and it does have a frequency. It has a limit of 31 hertz, 3100 hertz. Okay, 3.1 kilohertz or 4 kilohertz at most. If you send any more than that, it cannot take it. So 3100 hertz is the phone wire bandwidth. And now if you are going to use it where there is a noise such that the signal to noise ratio is 30 dB. Now you have to understand by now dB. I will be using dB now left and right. Now dB is what? Does anybody know what dB stands for? Decibel. And decibel is 10 times in upon out or something like that, right? So that's what it is. This is 10 times that. So 3 is the 10 times log of base 10. Now you have to keep track of that base also very clearly. When we defined the bell, it was log base 10. But we are using log base 2 for both Nyquist and Shannon. Right? So log base 10, signal to noise ratio, 30 means signal to noise ratio is 1000. Okay? Now people who work in this field, they just get used to this kind of translation. So in their mind, log base 10, if somebody says 10 dB, they know it's the ratio is just 10. They say 20 dB, the ratio is 100. Say 30 dB, the ratio is 1000. 40 dB, ratio is 10,000. They just get used to that multiplication. You will get used to it too by the end of this course. But basically, right now you have to calculate what is 30 dB. Other people don't think. People who are experts, they know 30 dB is a factor of 1000. Okay? So 30 dB is a factor of 1000. This is how. Alright, so basically the capacity is log base 2 1 plus S upon N. S upon N is 1000, and therefore you do all this math and it comes out 30 kilobits per second. 30.894 kilobits per second. Yeah.
How can we measure the noise?
How can you measure the noise? Yeah, so basically if you had a oscilloscope, you can see the noise. Basically, I mean, you can, whatever signal you receive, you subtract out the perfect sine wave from that and you get the noise. So you can see the noise in oscilloscopes.
So noise we will measure in what kind of unit?
Same unit as signal. So signal you measure in watts or, watts. And you measure the noise in watts, take the ratio. Right? So actually what we will do is we will not be using watts. Just when I said watts, I said, we really don't measure in watts. What we do is we measure everything in the unit is coming up in a minute. So I'm going to hold on to that one. Okay? What we do is we measure everything with respect to 1 milliwatt. So if you have 1 watt of power, with respect to 1 milliwatt, it is 1000 times. Right? So it is 30 dBm. So this is how the power is measured. Somebody says, well, the power is 30 dBm. That M is for milliwatt. dB is for decibel. So 30 dBm means 1 watt. Okay? Now, you should be quick and figure out if 30 dBm is 1 watt, how much is 40 dBm? Can somebody do this quick in their brain? 40 dBm would be 10 watts. Good. Alright, so you will get used to this multiplication and log scale working, soon. So they always work in log scale. They don't use watts. They just use dBms. Hamming. These are all big names. Now the Hamming says that if you take any two strings, the errors basically are the exclusive R. So basically, if you take this bit and you send this and you got that, you do the exclusive R and you count the number of ones, that is the distance between them. That is the Hamming distance. Okay? You can easily measure the Hamming distance. So now, the error correction. So basically, what we can do is, and I'm going through lots of wireless physical layer, communication theory quickly. So jumping from one topic to the next. Thing is, suppose you want to send 0, 0, and we can decide that whenever you want to send 0, 0, I will send 5 zeros. When I want to send 0, 1, I will send 0, 0, 1, 1, 1, 1. When I want to say 1, 0, I will send 1, 1, 0, 0, 1, and 1, 1, and so on and so forth. So, this advantage of this coding, error correction coding, this is actually error detection, error correction coding, is that if I received this 0, 0, 1, 0, 0, this is not one of the 4 codes that we agreed. Right? But what we received here has a distance from each of these 4 codes. These 4 codes can be put on a 5-dimensional space. And this one, we will find that it has a distance of 1 from 0, 0, 0, 0, all zeros. It has a distance of 2 from 0, 0, 1, 1, 1. Can you see that? Right? And distance of 4 and 3. So the most likely, these things would not have happened. This was the thing that you sent. 0, 0, 0, 0. Most likely. Right? And therefore you really sent a 0, 0. So this is a 0, 0. Yeah.
How are those code words created from the data?
Yeah, so that's the whole theory. Coding theory is a subject that will take several semesters. I will not go into that one. And we do it all the time. I learned it myself. But that's a field. And so coding theory will not go. But let's say we somehow, some expert coding theory person sat down and said this is the right code to use. Then basically we can do the error detection and correction, because when we receive this, we know that there is an error. Nobody will send that one. And then we can even correct it, because we can say it is 0, 0. So instead of 0, 1, 1, 0, 0, it is 5 zeros. Similarly, if you receive that, then you can figure out. In some cases, it is distance 2 from everything. So now you are not really sure. So it is same distance from 2 places. So it is equally distance from this and that. Now you cannot be sure which one it is. Right? So it can be detected but not corrected. So now we know that there is an error, but we cannot correct it. If it is close to something, we can say, okay, all right, most likely this is it. But if it is equally close from 2 different ones, then we have to say that this is detected but not corrected. And if there are 3-bit errors, they will not be detected. So you send that and you receive this, bad luck. It will just go through. And you will have to find some other method of detecting and correcting them, which we will talk about. But at this level, where people are sending bits, and these are the physical layer people, they have designed these mechanisms for their use, so that for every little bit that they receive, they can figure out that there is an error that can be corrected, and so on and so forth. So this is error correcting code, ECC. Okay? Yeah.
Is there like an optimal length of the word so that it's like efficient to the transmitter, but still it gives like enough?
Okay, so the optimal is your personal definition. The question is there an optimal length? So if you want to send 2 bits, if you code it into 3 bits, you get some performance and there is some cost. If you send it as 4 bits, there is better performance and more cost. If you send 5 bits, so it continuously goes like that, right? Now the question is, where is the optimal? How much money you have? And so basically that's what it is that at some point you say, I don't think I want to pay $100 for this little device, And so that is what it is. It's basically the more bits you send, the more performance you get. Of course, the thing is, we will see. Basically there are some formulas which tell you how much you get by increasing. So at some point you will say it's not worth the cost. Alright. So now we covered the bit pattern. Now we have to, I'm going to totally change the topic. Anything about modulation, coding, or anything like that we have talked about so far? Yeah?
So the errors more than the maximum Hamming distance will not be detected, yes?
Hold on. Question is, the error more than the maximum Hamming distance will not be detected. Hold on. If the Hamming distance in this particular coding, there is no such thing as maximum Hamming distance. In this coding, the maximum Hamming distance is 1. Basically 1 will be detected and corrected, 2 will be detected, 3 will not be detected. So what is the maximum Hamming distance? Maximum Hamming distance could be 5. There are 5 bits.
For this code word, in this example.
Right. So what she is saying is, among these 4 words, they have been located in this 5-dimensional space such that between any 2 words there is a minimum Hamming distance of 3, not maximum. Minimum Hamming distance of 3. So 0 and 0, 1, they are different by 3. These 2 are different by 3 and different by 3 and so on and so forth. So minimum Hamming distance is 3, and that actually is the important thing. Guys, if you know that the minimum Hamming distance is 3, you are in trouble. Right? You can't detect, you cannot correct. More than 3, you are in bigger trouble. I mean, you might be doing much more harm. Less than 3. Now you have to worry about 1 and 2. So 1 obviously, we always correct, we somehow believe that 1 is, quite possible and we just correct it. And 2, basically, then you have to see if the word that you receive is distance 2 from 1 and everybody else it is 3. Then, you might say, okay, all right, I will correct it. But if it is 2 from 2 different points, which is possible, in which case you won't be able to correct it. So what you do is you measure the Hamming distance of the received from the code. Right? We call it code book. So you measure the Hamming distance of the received word from the code book, and then you say, well, whichever looks like closest to it. And if there's nothing such thing as one closest to it, then we say, okay, we detect, but I can't be sure which one it is. Right? And if you go more than the minimum Hamming distance or equal to the Hamming distance, then you won't even know. Yeah.
Isn't the probability that you will be that very low?
Yeah, of course. So thing is, if probability of 1-bit error is p, 2-bit error is p square, and you so on and so forth, you multiply that. And the p, by the way, is 10 raised to minus 9. Okay? So if it is 10 raised to minus 9, 1-bit error. Okay, so what is the probability of 2-bit errors? I mean, it's very low. So and you say, okay, all right, I will take that probability. No. I am changing the topic to access method. So here is the problem. And this is particularly from the wireless point of view, because the medium is 1. So there is only one air here, and if I speak, you speak, they speak, we are all going to interfere. Right? So there are several ways to share this medium. One is time division multiple access, which means that we divide time. So when I am speaking, you don't speak. Right? And when you are speaking, I don't speak. And the way we do that is by raising hands. So that is what? Time division multiple access, TDMA. Right? That's what we do most of the time in life, TDMA. Right? But what if it is a party? If you did, there are 100 people in this room, right? If they did TDMA, that won't be very efficient or very interesting. Would you want to be in that party? Okay, I want to speak. Right? Now think about this. If everybody is speaking English, there is a lot more interference. If suppose some people speak Chinese, some people speak Arabic, some people speak, Iranian, Hindi, whatever, then everything goes on and there is no interference. Is that true? Because our ears filter out Chinese, my ear. They don't understand it, it doesn't matter, right? If you hear Chinese, you will figure out every word of it and your brain will start processing it right there and it will interfere with your thoughts, right? But if I speak Hindi, it won't interfere with your thoughts. So the thing is that we can tune ourselves to a particular language or particular coding, as we call it, and then you can filter out all other codes. Right? So there is a way to manage that, and that is it's called code division multiple access, CDMA. And that is what we use in parties. Actually, okay, so all right, I have lied a little bit because in most parties in America, they will probably be all speaking in English. But I'm just saying that will cause a lot more interference. If some people speak different languages, then it will cause less interference. Clear, right? So that's what we are going to see, that we are going to use CDMA most of the time from now on in wireless. Okay? Alright, so how do we design a code? So one way to design a code is frequency hopping. And frequency hopping works as follows. That I use this frequency for 50 millisecond, and then I will change my frequency to this one for 50 millisecond, and then to that one, to that one, to that one, And I'm not going to do it in a sequential, basically fixed order. I'm going to do it in a random order. Okay? And the way we do the random order is by using a random number generator. And the random number generator, the receiver knows. So let's say I want to talk to her, and I say, okay, here is my random number generator. And now I can keep talking, changing the frequency, and she will get the right frequency at the right time. But somebody else doesn't know the random number generator, will not be able to go to those frequencies. Right? So they will not be able to listen. They will not be able to tune. Actually, this was designed more for secrecy, for privacy, for military. Right? But now it has become a common method. And actually it was invented by Hedy Lamarr, who was an actress, and she was working on a piano, and something to do with the frequencies on the piano, she figured out that if we generated randomly, this we can do with this and that and that. And now it was then finally ended up with military, which we used for a long time, and now everything that we do today is kind of uses this. Frequency hopping spread spectrum. Now I haven't explained what is spread spectrum, but frequency hopping I have explained. Frequency hopping means that we change the frequency every so little time, after so time, randomly, and we know the random number generator. Right, yeah.
Could you still use this with frequency modulation?
Yeah, right. So during that time, when 50 milliseconds, I'm going to send you thousands of bits, and they will be using one of those QAMs. It could be frequency modulation, it could be QAM.
But if your frequency is changing, maybe I don't understand, are you still listening to it if you're tuning into a certain frequency?
Yeah, we continuously tune to the same frequency. So thinking I'm talking to you, right? And I tell you, look, I'm going to start at red frequency, and then here is a formula to calculate the next frequency, right? So you use that formula, the random number generator, and you figure out what is the next frequency. Now it's going to change to that frequency. You switch, I switch, both, sender and the receiver. Everybody else doesn't switch. Everybody else is, somewhere else. Yeah.
Actually, I think that this is for the carrier frequency. It's different from the beat frequency. Beat frequency will be over the carrier frequency, and the
Right. So what she is saying is, when we say frequency here, we are talking about how we are going to modulate, what we are going to modulate. On the top of that frequency, you can do lots of modulation, amplitude, frequency, QAM, and all that. Right? Okay. Second point is, the goal, actually one thing you can do is you can actually avoid the interference. That's what we are trying to do. We are trying to avoid the interference so that even if we both were, I'm talking to you on red and he's talking to her on red, they will collide. Right? But the next, that 50 millisecond, we will not collide. Because I will switch to something else, he will switch to something else. So there is some interference, but this will be kind of, gone quickly. So this random number generator is your code. Actually, random number generator is probably the same. You know how the random number generators work. In the random number generator, you put a seed and the next number comes out. You put that and you get the next number comes out. The seed is your code. You put a different seed than I put. Okay? If you put a different seed, you get a different sequence. I put a different seed, I get a different sequence. Is that clear to everybody? How the random number generators work? So basically, we all have a different code. That means a different seed. We all know the same random number generator. You can all use the same random number generator, but we have a different code, and therefore we can all talk at the same time in the same room. Okay? Makes sense? Yeah.
How bad is it for collisions between those? Like, do you have to completely repeat the message the next 50 milliseconds, or do you still sort of filter it out?
Yeah, right. So the thing is, if suppose two people spoke at the same time, how bad is the message? It depends. If I'm just talking at the same near to you at the same time, your ears will pop out. But if I'm here and you are there, they will not. So, there are other possibilities. So both people can talk at the same frequency, and then the interference will depend upon so many things. Right? But we are talking on the different frequencies, then then there are less things to worry about. All right. But if you were to plot the signal over a long time, normally the signals in a frequency look like this. They are at one frequency and the noise is everywhere. Sorry. Yeah, right. Signal is at one frequency and the noise is everywhere. But with frequency hopping, the signal is also everywhere. Right? Some power is here, some power is there, some power is there, some power is there. So this is why it's called spread spectrum. What we have done is, we have basically make the signal look like noise. Now it's everywhere. Okay? So this is called frequency hopping spread spectrum, FHSS. There is another way to spread the spectrum, or code, and that is very simple. Basically, you select a code, we select a code, and let's say we selected an code which is 0100101110. I think it is 11 bits. So we selected the 11 bits like this to be 0 and the opposite of that to be 1. And somebody else selected some other 11-bit number to be 0 and 1 and and so on and so forth. Everybody selects a different code. So whenever we want to send a 0, instead of sending one bit, we send 11 bits like this, and when we want to send a 1, we send 11 bits like that. So now, a lot of people can talk, and I am looking for this kind of bit pattern. If it is something any different than that, then we don't take it. We just reject it right there. Okay? So again, with different codes, many people can talk in the same room. So this is called code, basically direct sequence. This is called direct sequence spread spectrum, DSSS. Now this has the same effect for a spread spectrum. If you see the spectrum of this signal, normally with time, with big pulses, you will look like this. With this, it will look like that. It is spread. It's not at one place. Okay? So that's why it is direct sequence spread spectrum. So the signal bandwidth is much larger than the data bandwidth. So your data has only 1 bit per second, but the signal has 11 bits per second. Actually cycles or whatever way you want to measure it. It will be a lot more. You are sending 11 times more information. So that is called direct sequence spread spectrum. Alright, so we now heard two different spread spectrum techniques. Now all of these words will be used when we talk about Wi-Fi, Bluetooth, LTE, WiMAX, because all of these use these things. For example, just to give you an example, Bluetooth uses frequency hopping spread spectrum. So when I have Bluetooth on, which is on right now, and your Bluetooth is on, which is on right now, they're all hopping all over. Okay? And so frequency hopping is very common now. And DSS is very common now. Wi-Fi uses quite a bit of that. Okay? I'm introducing all these terms so that when we come to really Wi-Fi, describing Wi-Fi, and I use the word frequency hopping, you know what it is. Doppler shift. Basically, what it is that the frequency, how it sounds to you, depends upon this frequency, basically. I mean, if somebody speaks at a, like I mentioned, a very common fact is that the female voice has higher frequency than the male voice, right? And so when you hear, your ears figure out what frequency it is, and it figures out whether it is a male or a female, right? Now the interesting fact is, so you just measure, your brain measures the cycles per second and figures the frequency, figures out the frequency. Now the interesting thing is, if you are driving in a car, moving, then what will happen is, when you are moving towards the source of the sound, you are going to get more cycles per second than that being transmitted. Does that sound like common? I mean, this is what is being transmitted, but if you are coming, you will get more cycles per second because you are just moving towards the source. On the other hand, if you are moving away from the source, you will get less cycles per second. Right? So the same sound will sound different, and then you will know whether the train is coming towards you or the train going away from you. How do you know? Because the frequency changes. That is the Doppler shift. Right? If you hear a sound and it looks like the frequency is going up and up and up, then you know that something is coming towards you. On the other hand, you are standing right there, but the frequency is going down and down and down, then you know something is going away from you. So that's how you know whether the train is coming or going, or bus is coming or going, or you are coming or going, whatever it is that is moving. Right? And so Doppler shift is very easy because basically the frequency difference, the change in frequency is simply your velocity divided by the wavelength. If you are going, suppose the wavelength is 5 meters, and if you are going 5 meters per second, you are going to get 5 meters more, 1 cycle per second more. Right? Common sense. So what you do is you find your velocity in meters per second and find the wavelength in meters and divide that, and you get basically the difference. All right. So here is an example. This says nu f divided by c. So let's say take the example first of all. So let's say we use 2.4 gigahertz. Okay, and that is equal to 12.5 centimeters. We had calculated that before, by the way. I forgot to do one thing. I should have given you homework so that given a frequency, you should be able to calculate the wavelength. Right? This is the homework for today anyway. It's coming up in a minute. But basically, I should have given you last week. So, given that it is 2.4 gigahertz, that is the frequency your Wi-Fi uses, by the way. That is the frequency that your Bluetooth uses. That is the frequency we all use in everything that we use at home, including your phone, by cordless phone. So 2.4 gigahertz is a very common frequency. It has a wavelength of 12.5 centimeter, which I have written here as 0.125 meter. Okay, you can calculate the wavelength. Now, if you are going at 120 kilometers per hour, you can calculate that, translate that to 33.3 meters per second. Right? So the frequency difference is simply velocity, which is 33.3, divided by the wavelength, 0.125, is 267 hertz. So the frequency will be 267 hertz different than what it is being sent at, depending upon whether you are going towards it or away from it. Is that clear? How the Doppler shift is created? You have to calculate the wavelength, and wavelength tells you how many cycles you can get in that with that speed more than if you are not going at all, not moving. And it doesn't matter who moves, the source or yourself. If the source is moving, you are stationary, you are going to get more or less cycles. Yeah.
So if you're on your cell phone in your car and you're transmitting and receiving data, like how does it know how fast you're going?
Exactly. So basically what it is they can figure it out that you're going at 120 miles per hour and give you a ticket right there. Yeah, so that actually will come up. When we talk about mobiles, basically the thing is we have to be, if you are going to do anything with the frequency and your frequency is going to change, then I have to be allowed for the possibility of you moving at 120 kilometers per hour, because that's a normal speed. 120 kilometers I think is 60 miles per hour. Something like that. Anyway, so the idea is that is the speed which people are going to go in the car, and so their frequency could be off by, so much, and so I have to be able to forgive that. Okay? All right. Now, what if there's a reflector? So you are driving around a mountain, having nice scenery, and you are also getting a cellular signal. You're going to get two signals. You're going to get direct signal, And if you're driving in this direction, then you will get less frequency than what is being transmitted, but you will also get a reflected signal. And its frequency will be increasing because you're going towards it. Right? So two rays will be received, and the difference between those two would be 2f v upon c, 2 times the Doppler shift. V is the velocity. I was saying mu before, so that was wrong. If v is the velocity, which is what is speed you are going, c is the speed of light, and f is the frequency. So anyway, so it will be 2 times the Doppler shift. And so they will add or cancel out each other as the receiver moves. So coherence time is the time at which the channel response is constant, and so that is called 1 upon the Doppler spread. So what happens is, basically what if you measure this for some time, the two waves will add, and for other times they will be out of phase. So, and sometimes they will be in phase, and sometimes they will be out of phase, right? So they will add, and sometimes they will subtract. All right, but there is some slight period over which, let's say they add and then they subtract. So that time is called coherence time, right? And that will be just opposite of the difference. So whatever is the Doppler spread, which is 2 times the Doppler shift. Okay, Doppler shift we calculated before. Twice that is called Doppler spread because plus and minus, and 1 upon that spread is called the coherence time, during which it will always be adding, and then it will subtracting for another coherence time, and then adding, right? So the channel response is one way. During that time is called coherence time. So we will use that term, coherence time, Doppler spread, Doppler shift, and the relationship is clear now, right? Doppler shift is Fv upon C. Spread is 2 times Fv upon C, and the coherence time is 1 upon 2 Fv upon C, whatever. Any question about the Doppler? Yeah.
So there is no difference that which of these signals is filtered out?
Which among these two signals?
Yeah.
Oh yeah, actually, so they will have a different magnitude for sure.
Yeah.
If this is one transmitter, and then we will talk about that multipath in a minute. So that is a different lecture coming up. Now duplexing. It's a totally different concept. Duplexing is basically the directions which the traffic goes. Now what we could do is, we could have 2 frequencies. On one frequency subscriber talks to the base station, blue frequency. On the other frequency, the base station talks to the subscriber. Now both of them can talk at the same time. And that would be frequency, basically frequency division duplex, FDD. This is called FDD because, first of all, we are frequency division full duplex actually here. Full duplex means, okay, so everybody understands full duplex and half duplex, right? Somebody doesn't know half duplex? Let me explain. So if you go on the road here outside, big road, what is the name of the road?
Forest Park Parkway.
Huh?
Forest Park Parkway.
Forest Park Parkway. So the traffic can go in both directions. So that is called full duplex. But if suppose one side is closed because there is an accident or they are making construction, then what happens? Then they close one side and then they put by a guy with a flag, says stop, you cannot go. And then one side goes and then they put a flag on the other side and the second side goes, right? So that is called half duplex because still the traffic is two-way, but it is alternating. Half duplex. Or full duplex means you can go at the same time. So this is full duplex. On the top is full duplex. However, we could also do so that we could do half duplex, so that we could do for some time base station talks and then the subscriber talks and the base station talks and subscriber talks. So this half duplex is called TDD. TDD means time division duplexing. The two sides divide the time. In FDD, two sides divide the frequency. Right? We call it full duplex. FDD and TDD is now. Now in the TDD, in FDD, basically the frequencies don't have to be equal. I mean, you could give 100 megahertz to the base and 10 kilohertz to the subscriber. Similarly, the time division duplexing, the time does not have to be equal. You could give as much time to the base as you want and less time to the subscriber and vice versa. Right? So that is TDD, FDD. So the most new technologies use TDD. And we talked about, remember TDD, LTE, time division LTE other day. That is because now the traffic is very asymmetric. Because we listen to video, we watch more video than we transmit our video, and therefore there is more going in one direction, and so that can be easily done with TDD. If you want to watch video, we start giving more time to the base station. If you want to talk, then we start giving more time to you, or something like that, right? With FDD, you cannot change that. Frequencies, once it is allocated, it is allocated. I mean, like frequencies, generally they keep equal, by the way. So when FDD, what they do is they give you 30 kilohertz on this side, 30 kilohertz on this side, and then you just cannot make it 300 on one side. Okay? So FDD is kind of static. TDD is dynamic. The word dynamic means time changing, which is, it is, right? So TDD is what we need for tomorrow's network. For yesterday's network, where we were all talking on the phone it is 50-50. I talk 50, you talk 50. If you talk 100, then, we're not very good friends. But, so basically it is 50-50, 50 coming down, 50 going up. Right? In video, it is not the case. Yeah.
If you had a peer-to-peer system for video, you'd probably prefer the FDD, right?
Yeah. So the thing is, FDD, if you prefer means, basically if you have a peer-to-peer system, yes, it would be good because then, that's why they're trying to make it remember we talked about this, that P2P video is coming in because the network that were designed for symmetric traffic, they cannot take this asymmetric traffic. So they can make it more symmetric by putting P2P. Although in P2P, everybody lies. Now remember, those of you who do P2P, you don't send out at 2 gigabits per second, you send out at 40 kilobits per second and you receive at 2 gigabits per second, right? So it is still asymmetric. And the reason it is still asymmetric is because that is how the networks are designed. If you think about not the telephone networks, but if you think about DSL is asymmetric. Right? So a lot more can come to you than can get out from you. Upload speed is very low. So when you get a DSL connection from AT&T, you only can send 500 kilohertz, while you can get 5 megabits. You can send 5 kilobits. So 1:10 ratio. So that's why you don't want to upload at symmetric rate. So here's the thing: you can design a network for symmetric traffic. You can design a network for asymmetric traffic, and then you have to match the traffic to the network that is designed for. Right. So that's the point. Okay. All right. The point here is that it says most WiMAX. I should change it. Most LTE deployments will use TDD because you can quickly change up and down rate. Having said that, it turns out in practice you cannot change it. And I will come to that when we talk about TDD, LTE, whatever. So then we'll see as to why it cannot just change it. Yeah.
I'd like to ask you, I think then frequent FDD is better for gaming videos than the TDD.
Is better for?
Gaming videos.
Gaming?
Yeah.
Because gaming is more symmetric?
Yeah, I think because...
Yeah. I mean, basically FDD is past, TDD is future. The past was voice. Right? So that is where all the previous networks were designed for FDD. Period. That's it. So your old telephone network at home, your old telephone network on the cellular, everything was designed for FDD. Right? All the traffic was voice. But with the internet coming in, the ratios are changing. So then we are thinking about TDD. Okay? Alright, so TDD does not require prepared spectrum. With FDD, you need twice the frequency. Here with 30 kilohertz, you can both talk, right? And easy channel estimation. And there is another advantage of this is that now when you receive this, you know that how much noise there is, and then you can change your transmission to match that noise. Here, you don't know how much noise it is because you never receive your own signal. When you don't receive the signal. Basically what is happening is, I am transmitting at this frequency, so this guy is getting the noise, but we don't know how much that noise is. Well, I am receiving at this frequency, so by receiving signal, I cannot figure out what is the noise. Here I know because we are both transmitting on the same frequency. Right? So we both see the same noise. Right? So this is better in that sense. Easy channel estimation. Channel estimation means figuring out what the channel is. Negative is all neighboring BSS to time synchronize. So then the problem is that if there are two base stations and one says I want to transmit and this one says I want to transmit, there is some complex interference between them, and so you cannot be, so there is a problem there which we will talk about when we come to that point. Okay? Yeah, a question? Alright, so that brings us to the end of this on the last minute. Basically 5 key points. Electric, radio, light, X-rays are all electromagnetic waves now. You know that, right? And wireless radio waves travel at the same speed of light, and the wavelength can be calculated by lambda is equal to C upon S. Third thing we learned was QAM. So we now know 16 QAM uses 16 combinations. That means 4 bits per symbol. And hertz and bits are related by Nyquist and Shannon's theorem. The Nyquist just doesn't worry about the noise, it just worries about the levels of your signal. And the Shannon's worries about the noise, and those are the limits. And frequency hopping and direct sequence we talked about, those are the CDMA methods. Right? Now, there is a homework, and this is due next Monday. Alright? And so you need to practice all about how to calculate the wavelength, how to calculate the power, and here's the dBm. This is how we measure the power, 30 dBm, 20 dB, and so on and so forth, right? And that's the end. Any questions?